Imagine standing inside a furnace so hot that atoms themselves come apart. Not just any furnace, but one that's been burning steadily for 20 million years, converting simple elements into complex ones through the pure alchemy of nuclear fusion. And now, after all that time, after all those eons of patient burning, you're about to witness its final day. Hello and welcome to the Sleepy Astronomer. Tonight, we're not travelling outward to distant worlds or looking up at the night sky. Instead, we're journeying inward, deep into the heart of a dying star. A red supergiant 15 times more massive than our Sun, reaching the end of a life that has spanned longer than human civilization, longer than complex life on Earth, longer even than our planet's continents have held their current shapes. If you're settling in for the first time, welcome to this gentle exploration of the cosmos. And if you've drifted with me before through the quiet corners of space, it's wonderful to have you back among the stars. Whether you're tucked into bed, curled up on your favourite chair, or perhaps lying somewhere comfortable where you can let your mind wander, I'm so glad you're here. Our journey tonight follows a paradox that sits at the very heart of existence. We're going to witness destruction on a scale almost beyond imagining, and yet that destruction is precisely what makes life possible. The star we'll explore tonight, in its final violent moments, will forge the heavy elements that make up your bones, your blood, the device you're listening on, and the planet beneath your feet. Death and creation bound together in the most intimate cosmic dance. For billions of years, this star has been fighting a quiet battle. Gravity, patient and relentless, constantly trying to crush the star down to nothing. Nuclear fusion, fierce and energetic, pushing outward with the pressure of billions upon billions of nuclear explosions happening every second. These two forces have been perfectly balanced, holding the star in what physicists call hydrostatic equilibrium. But like all truces, this one cannot last forever. Ancient peoples across the world witnessed the sudden appearance of brilliant new stars in familiar constellations. The Chinese called them guest stars, carefully recording their positions and brightness. Arab astronomers noted them with wonder. Indigenous cultures saw them as cosmic omens, messages from the ancestors, or the birth cries of new spirits. They couldn't have known they were watching the final moments of stars like ours, explosions so powerful they could briefly outshine an entire galaxy of hundreds of billions of suns. There's a strange beauty in stellar death. It's not a fading, not a gentle dimming like a candle burning out. It's a transformation, a moment of spectacular creativity disguised as destruction. In the final seconds of collapse, temperatures and pressures reach levels that haven't existed in the universe since moments after the Big Bang itself. And in those extreme conditions, something remarkable happens. Elements that could never form during a star's normal life suddenly crystallize into being. Gold, platinum, uranium, the heaviest elements in the periodic table, forged in the crucible of stellar death. Tonight we're going to slow down time. We're going to stretch out the final day in the life of a star and walk through it hour by hour, watching as silicon burns to iron, as the core collapses in on itself, as the shockwave tears outward through layers of stellar atmosphere, and finally as the star's substance scatters into space, seeding the cosmos with the raw materials for future worlds and future life. So, settle in, let your breathing slow, and prepare to witness something that actually happened countless time in the distant past of our universe. Every atom in your body heavier than hydrogen was forged in moments like these. You are quite literally made of star stuff, and tonight you'll understand exactly how that ancient stellar fire became you. Take a deep breath, and let's descend into the heart of a dying star, where the final dawn is just beginning to break. Let's set our clock to 6 in the morning on the final day of our star's life. Not a morning as we know it, of course. There's no sunrise here in the core, no birdsong, no gradual brightening of the sky. But if we're measuring time in the life of a dying star, this is the beginning of the end, the silicon burning stage, the false dawn before the real darkness comes. Deep in the core, about 20,000 kilometers down from the star's visible surface, the temperature has climbed to 3 billion degrees Kelvin. To put that in perspective, the core of our Sun sits at a relatively comfortable 15 million degrees. The surface of the Sun, the part that warms your face on a sunny day, is a mere 6,000 degrees. This star's core is 200,000 times hotter than that. It's so hot that if you could somehow observe it directly, the light it emits wouldn't be visible at all. It would be pure gamma rays, photons so energetic they could pass through your body like it wasn't even there. At these temperatures, something remarkable is happening. Silicon nuclei, each containing 14 protons and 14 neutrons, are slamming into each other with such violence that they fuse together. Not directly into something twice as large, mind you. Nuclear fusion at this level is more like a carefully choreographed dance than a simple collision. Silicon captures an alpha particle, which is just a helium nucleus, 2 protons and 2 neutrons bundled together. Silicon-28 becomes sulfur-32. Sulfur captures another alpha particle and becomes argon-36. Argon becomes calcium, calcium becomes titanium, titanium becomes chromium. Step by step, alpha particle by alpha particle, the core is climbing up the periodic table. It's the stellar equivalent of walking upstairs, each step requiring more energy, each step producing slightly less energy than the one before, and at the top of those stairs, waiting patiently, sits iron 56. Iron is special. If you were to graph the binding energy of atomic nuclei, the amount of energy it takes to hold all those protons and neutrons together, you'd get a curve. That curve rises from hydrogen, climbs through carbon and oxygen and silicon, peaks at iron 56, and then starts to descend toward the heavier elements like lead and uranium. Iron sits at the top of that curve. It's the most stable nucleus in the universe. Fusing anything into iron releases energy. Fusing iron into anything heavier requires energy. For a star, that's a problem. Actually, it's the problem. The star's entire existence has been predicated on a simple transaction. Fuse light elements into heavier ones, release energy, use that energy to push back against gravity's inward squeeze. For 20 million years, this star has been running that transaction successfully. Hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon. Each stage producing enough energy to keep the lights on, so to speak. But iron changes the rules. Once you've made iron, the game is over. There's no more energy to extract. It's like trying to get blood from a stone, or, in this case, trying to get fusion energy from the most stable nucleus nature allows. If we could somehow see inside the star at this moment, we'd witness something that looks almost like a planetary system in reverse. Instead of planets orbiting a sun, we'd see shells of different elements arranged in layers, all surrounding that growing iron core. On the outside, the star's envelope is still mostly hydrogen and helium, blissfully unaware of the crisis brewing deep below. Moving inward, we'd pass through a shell where hydrogen is still fusing into helium, then another where helium fuses into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. And at the very centre, like the pit of a cosmic peach, sits the iron core, growing, waiting. The core at this stage is about the size of Earth, but it contains more mass than our entire Sun. Imagine compressing the Sun down to something the size of our planet. The density is beyond anything we experience in daily life. A teaspoon of this material would weigh about as much as a cruise ship. If you could somehow stand on the surface of this iron core, not that you could, the gravity would be so intense that you'd be flattened into a layer of atoms a few molecules thick before you could even process the thought. But here's the strange thing. Despite the gathering crisis, despite the fact that the star is running out of fuel, despite the iron core growing larger every second, the star's outer layers don't know anything is wrong. They're still shining away, still fusing lighter elements in their shells, still radiating energy into space. From the outside, if you were an astronomer observing the star from a distant planet, it would look perfectly normal. Perhaps a bit bloated, perhaps noticeably red from its expanded cooler surface, but otherwise unremarkable. This is what I mean by false dawn. There's a sense of things proceeding normally, of business as usual. The star is still technically alive, still maintaining the delicate balance between gravity and pressure that defines stellar life. But deep in the core, in that Earth-sized sphere of iron, the balance is starting to tip. Ancient cultures had a deep understanding of false dawns, even if they didn't know about stellar physics. The Celts spoke of the banshee, whose wail announced death before it arrived. Not death itself, but its harbinger, its warning. In Irish mythology, hearing the keening of the bean sea meant that death was approaching, that the veil between worlds was growing thin. The silicon burning stage is the star's banshee wail, an announcement that something profound is coming. The Greeks personified dawn as Eos, a goddess who rose each morning to open the gates of heaven for the sun's chariot. But Eos was a complex figure in mythology. She brought light, yes, but she also brought sorrow. She was cursed to fall in love with mortal men, watching them age and die while she remained eternally young. There's something poignant in that, something that echoes in our dying star. The dawn is coming, light is coming, but it's a light born from loss. In Hindu philosophy, there's the concept of Kala, which means time, but also death and change. Kala is both a creative and destructive force, the power that brings things into being and the power that takes them away. The god Shiva dances the Tandava, a cosmic dance that simultaneously destroys the universe and prepares it for renewal. Silicon burning is the star's Tandava, a final creative act that sets the stage for its own destruction. The time scales here are worth pausing to appreciate. Our star has been burning hydrogen for about 20 million years. That's a long time by human standards. 20 million years ago, Earth's continents were still slowly drifting toward their current positions. The ancestors of humans were small, tree-dwelling primates. 20 million years is enough time for mountains to rise and erode, for species to evolve and go extinct, for entire epochs of geological history to unfold. The helium burning stage that came next lasted perhaps 2 million years. Still an unimaginably long time, but noticeably shorter. Carbon burning, the stage after that, lasted only about 12,000 years. Neon burning lasted just a few years. Oxygen burning, the stage immediately before silicon, lasted only months. And now silicon burning, the final meal, the last source of fusion energy available to the core. How long does it last? Days, perhaps hours. The star is accelerating toward its end like a ball rolling down a hill that gets progressively steeper. Each fusion stage provides less energy and lasts for less time than the one before. It's a countdown that's been running for 20 million years, but only now, in these final hours, does the pace become breathless. Imagine living your whole life at a normal pace, decades passing with a regular rhythm of seasons and years, and then suddenly finding yourself in the last day of your life where hours pass like seconds. That's what the star is experiencing now. Geological time is compressing into human time, and soon, very soon, it will compress into something even faster. Medieval alchemists, in their endless quest to transmute lead into gold, believed in a process they called the Great Work. The materia prima, the base matter, had to be heated and processed through various stages, each one bringing it closer to perfection. Nigredo, the blackening; albedo, the whitening; citrinitas, the yellowing; and finally, rubedo, the reddening, which produced the philosopher's stone, and with it the power to transmute any metal into gold. They were wrong about the details, of course. You can't make gold in a flask through chemical processes alone, but they were onto something profound about transformation requiring destruction, about creation emerging from dissolution. Our star is performing the real great work, the actual transmutation of elements, not lead into gold through mystical processes, but silicon into iron through nuclear fire. And soon, in the stellar explosion to come, iron into gold through processes even more extreme. There's something almost tragic about iron accumulating in the core. Each iron nucleus that forms is like a tiny weight being added to a scale. The star has been balancing gravity against nuclear pressure for millions of years. But now, with every atom of iron that's created, the scale tips a little more toward gravity's side. Iron doesn't help. It just sits there, dense and inert, refusing to fuse, refusing to provide the energy that the star desperately needs. The core temperature is still climbing, driven by gravitational contraction. As the iron accumulates, as the core's mass increases, gravity squeezes harder. And when gravity squeezes, temperature rises. It's a fundamental law of thermodynamics, the same principle that makes a bicycle pump warm when you compress air. The star is trying, desperately, to find a way to make iron fuse. It cranks up the temperature to 4 billion degrees, 5 billion higher. But iron doesn't care. Iron is already at the bottom of the energy well. There's nowhere else to go. If stars could feel frustration, this one would be experiencing it now. For 20 million years, fusion has been the answer to every problem. Core getting too dense, fuse some hydrogen, release energy, push back, temperature dropping, contract a bit, heat up, resume fusion. It's been a reliable cycle, a thermostatic control system that has kept the star stable through eons. But now, for the first time in its existence, fusion is failing to solve the problem. The harder gravity squeezes, the more iron forms. The more iron forms, the less energy is produced. The less energy is produced, the less pressure pushes back against gravity. It's a vicious cycle, a feedback loop that has only one possible outcome. Native American traditions from various tribes speak of stars as ancestors, beings who have completed their journey on Earth and ascended to the sky. The sudden appearance of a new bright star was sometimes interpreted as a great leader or shaman making their transition, preparing for a journey to the spirit world. The Pawnee, in particular, had rich star lore, seeing the stars as people who had gone before, watching over those still on Earth. There's a beautiful parallel here. Our star is preparing for its journey, gathering its strength for one final transformation. The silicon burning stage is the moment of preparation. The quiet before the journey begins in earnest. In Japan, there's a concept called mono no aware, often translated as the pathos of things, or the bittersweet awareness of impermanence. It's the feeling you get watching cherry blossoms fall, knowing their beauty is fleeting. The Japanese aesthetic tradition values this awareness, this acceptance that all beautiful things must end, and that their ending is part of what makes them beautiful. Silicon burning is the star's mono-no-aware moment. The core is doing what it's always done, fusing elements, climbing the periodic table, but there's an awareness, if we can anthropomorphize for a moment, that this is the last time. After this, there is no next stage. After iron, the rules change completely. As we watch these final hours of silicon burning, as gamma rays cascade through the core and alpha particles slam into nuclei with devastating force, it's worth remembering that this exact process happened somewhere in our cosmic neighborhood about 4.6 billion years ago. A massive star, perhaps not so different from this one, went through its own silicon burning stage. It accumulated its own iron core, and when that star finally exploded, it scattered its newly forged elements into a cloud of gas and dust that was just beginning to collapse into our solar system. The calcium in your bones was forged in silicon burning in those final hours before a stellar collapse. So was the iron in your blood. Every breath you take, every thought you think, every heartbeat that pulses through your veins is powered by atoms that were created in moments exactly like this one, in the cores of dying stars, billions of years ago. The false dawn is breaking, the silicon is burning, the iron core grows heavier by the second, and deep in the heart of our star, gravity is beginning to smile. 3 hours have passed since we began watching. 3 hours of furious nuclear fusion, of silicon transforming into sulfur, argon, calcium, titanium, chromium, and finally, inevitably, iron. 3 hours that represent the very last of the star's 20-million-year life, where anything resembling normal stellar processes are occurring. The core now contains about 1.4 solar masses of iron. That's a specific number, and it's important. The physicist Subrahmanyan Chandrasekhar calculated in the 1930s that there's a limit to how much mass can be supported by electron degeneracy pressure, the quantum mechanical force that keeps dead stellar cores from collapsing. That limit is about 1.4 times the mass of the Sun. Our star's core is approaching that limit. Soon, very soon, it will cross it. The false dawn is ending. The real darkness is about to begin. It's 9 in the morning now, if we're still keeping time by our cosmic clock. The silicon burning has slowed to a trickle. The iron core has grown to 1.4 solar masses, right at that critical threshold we mentioned. And something remarkable, something almost perverse, is happening in the heart of our star. The iron is just sitting there. After 20 million years of constant nuclear fusion, after eons of elements transforming from one to another in a cascade of energy release, the core has finally produced something that refuses to play along. Iron 56, the most stable nucleus in the universe, the end of the line. Imagine spending your entire life climbing a mountain, finding new paths, new routes to higher ground, and then suddenly discovering that you've reached the summit. There is no higher. This is as far as fusion can take you. The temperature in the core has now reached 10 billion degrees Kelvin. To put that in perspective, that's hotter than the core temperature of our Sun by a factor of about 700. If you could somehow extract a cubic centimetre of this material and place it anywhere on Earth, the heat it radiated would vaporize everything within hundreds of kilometres. It would make the Sun seem cold by comparison. And yet, despite these unfathomable temperatures, despite the furious motion of particles slamming into each other at significant fractions of the speed of light, the iron won't fuse. Can't fuse, really. the laws of physics won't allow it. Fusing iron into anything heavier requires adding energy rather than releasing it. It's like trying to run a car uphill by letting it roll downward. The analogy doesn't work because you're going in the wrong direction. The core is now denser than anything you've ever encountered. We're talking about densities of about 1 billion grams per cubic centimetre. A sugar cube of this material would weigh about as much as a battleship. Actually, that's not quite right. A sugar cube of this material would immediately collapse through the floor, through the Earth's crust, and keep falling toward the planet's core, its immense gravity pulling everything around it into the hole it creates. At these densities, atoms as we know them don't really exist anymore. The space between atomic nuclei, the vast emptiness that makes up most of ordinary matter, has been squeezed away. Electrons, which normally orbit at comfortable distances from their nuclei, like planets around a sun, are now being crushed inward. This creates what's called electron degeneracy pressure, a quantum mechanical effect that emerges when you try to pack electrons too closely together. Here's where things get interesting. Electron degeneracy pressure isn't like normal pressure. Normal pressure depends on temperature. Heat something up and it pushes back harder. Cool it down and the pressure drops. But degeneracy pressure doesn't care about temperature. It's a purely quantum effect, arising from the Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state. Think of it like trying to fit people into a crowded elevator. Normal thermal pressure is like everyone moving around, bumping into each other, pushing back when squeezed. Degeneracy pressure is like the fact that two people simply cannot occupy the same physical space, no matter how much you compress them. The elevator can only fit so many people, and after that, the laws of physics say no more. For white dwarf stars, stellar remnants about the size of Earth but with the mass of the Sun, electron degeneracy pressure is enough to hold the star up against gravity forever. Well, not quite forever, but for timescales longer than the current age of the universe. White dwarfs slowly cool and fade, but they don't collapse. Our iron core, though, is approaching the limit of what electron degeneracy pressure can support. Remember that magic number, 1.4 solar masses, the Chandrasekhar limit. The core has been edging toward this boundary for hours now, adding iron atom by iron atom, like someone slowly adding weight to a straining rope. And here's where the situation becomes truly dire. As gravity squeezes the core harder and harder, the temperature climbs even higher. 10 billion degrees becomes 11 billion, 12 billion. The core is desperately trying to find a way out, some new fusion reaction that will release energy and push back against gravity's relentless squeeze. In this extreme environment, something strange starts to happen. The gamma rays, the high-energy photons that fill the core, become energetic enough to actually break iron nuclei apart. This process, called photodisintegration, is the reverse of fusion. Instead of nuclei combining to release energy, they're being torn apart, which requires energy. Each iron nucleus that breaks apart consumes energy that could have been used to support the core against gravity, energy that took billions of years of stellar evolution to create through fusion, and it's being consumed in seconds, used up to undo the very nuclear reactions that created the iron in the first place. It's like building a house over decades and then having to burn the furniture to stay warm, except in this case, burning the furniture doesn't actually keep you warm, it just delays the inevitable cold. The pressure inside the core begins to drop, not dramatically, not all at once, but steadily, inexorably. The core starts to contract, and as it contracts, the density increases, the temperature rises, and more gamma rays become energetic enough to photodisintegrate iron. It's a runaway process, a feedback loop spiralling toward catastrophe. There's another process happening alongside photodisintegration, something called neutronization. At the extreme pressures and densities in the core, electrons are being forced into protons. Normally, electrons and protons keep their distance. They're like opposite ends of a magnet, attracted to each other but maintaining a stable separation. But when you compress matter to these densities, you can actually force them together. When an electron and a proton combine, they form a neutron and release a neutrino. The neutron stays in the core, but the neutrino, that ghostly particle that barely interacts with anything, shoots out of the star at the speed of light. And here's the problem. Neutrinos carry energy. Each neutronization reaction removes energy from the core, energy that could have been supporting the star against gravity. Imagine trying to hold up a heavy weight while someone keeps removing pieces of the floor beneath your feet. That's what's happening to our star's core right now. The supports are being removed, bit by bit, as neutrinos stream away into space, carrying the core's energy with them. In mythology and folklore across cultures, iron has always held a special place. It's the metal of endings, of boundaries, of the barrier between worlds. In Celtic lore, iron is the one substance that fairies cannot touch or cross. Iron horseshoes over doorways, iron nails in pockets, were protection against the otherworldly. The fair folk, for all their power, stopped at iron's threshold. The ancient Norse had a different take. In their cosmology, the world would end in Ragnarok, preceded by the Fimbul winter, a long winter of iron and snow, 3 winters with no summer in between, a time of hardening and cold before the final battle. Our star's iron core is its own kind of Fimbul winter, a cold gathering of inert material before the final conflagration. The Romans associated iron with Mars, the god of war, not just because iron made good weapons, though that was certainly part of it, but because iron represented endings, the final resolution of conflict through violence. There's something fitting in that. Our star's iron core represents the end of nuclear fusion, the final resolution of the battle between gravity and pressure through catastrophic collapse. In Hindu cosmology, we live in the Kali Yuga, the Iron Age, the age of darkness and decline that precedes the destruction and renewal of the world. It's the last of 4 ages, each progressively more degraded than the one before. The Golden Age, the Silver Age, the Bronze Age, and finally the Iron Age, where virtue is at its lowest and destruction approaches. Our star has passed through its own ages. Hydrogen burning was its golden age, helium its silver, and now it sits in its iron age, waiting for the end. The symbolism runs deeper than ancient peoples could have known. Iron really is the end of the stellar road, the point where the rules change completely. It's not just a metaphor, it's physics. Let's pause for a moment to appreciate how strange this situation is. The star has been successfully managing its energy budget for 20 million years. It's been converting mass into energy according to Einstein's famous equation, E=mc², using that energy to shine and to support itself against gravity. It's been incredibly efficient. Every kilogram of hydrogen that fused into helium released enough energy to power a large city for several years. But now the equation is running backwards. Photodisintegration is converting energy back into mass. Neutronization is removing energy from the system entirely. The core is no longer an energy-generating powerhouse. It's become an energy sink, a black hole of thermodynamics, though not yet a real black hole. The core's temperature is still climbing, driven by gravitational contraction. We're approaching 15 billion degrees now. At these temperatures, the thermal energy of individual particles is enough to break apart not just iron, but progressively lighter elements too. Silicon nuclei are coming apart. oxygen nuclei are fragmenting back into helium. It's as if the star is watching its own history run in reverse, billions of years of element building being undone in minutes. Alchemists throughout history dreamed of the philosopher's stone, a substance that could transmute base metals into gold and grant eternal life. They worked with crucibles and furnaces, trying combinations of materials and procedures that seem almost random to modern eyes. They failed, of course, at least in their stated goals. You can't make gold from lead through chemical processes. But here's the thing they intuited correctly. Transformation requires extremity. The alchemical texts speak of mortification, of the putrefaction and death of the base matter, before it can be reborn as something purer. The negredo, the blackening, where all the colours disappear and everything becomes formless and void. Only through this dissolution could the work proceed to its completion. Our star is undergoing its own negredo. The iron core, the final product of millions of years of fusion, is being dissolved. Not chemically, but physically, as photodisintegration tears nuclei apart and gravitational pressure crushes electrons into protons. Everything is breaking down, becoming formless, approaching a kind of nuclear chaos. And just as the alchemists believed that true transformation could only come through this dark night of dissolution, our star's iron tomb is actually the necessary precursor to the most spectacular transformation in the universe. But we're getting ahead of ourselves. That comes later. The neutrinos are streaming out now in vast numbers, trillions upon trillions of them every second. If you were somehow standing near the star, not that you could, these neutrinos would be passing through your body by the billions every moment, but you'd never know it. Neutrinos interact so weakly with matter that they can pass through the entire Earth without touching a single atom. They're the ghosts of the particle world, present but intangible. Yet for all their ghostly nature, neutrinos are having a very real effect on the core. Each one carries away a tiny amount of energy, but there are so many of them that the total energy loss is staggering. It's like a crowd of people each taking a single grain of sand from a beach. Any one grain doesn't matter, but if enough people take enough grains, eventually the beach disappears. The core pressure is dropping more rapidly now. We're approaching what physicists call the point of no return, though that's something of a misnomer. There's been no return possible since the silicon burning started, really. This is just when the consequences become unavoidable. Think about standing on a diving board, walking toward the end. For most of your walk, you could still turn back. You could change your mind, step backward, return to solid ground. But there's a point, usually right at the edge, where your weight shifts past the balance point, and suddenly turning back is no longer an option. You're committed. You're going into the water whether you want to or not. Our star's core is at that edge right now, teetering on the balance point. Gravity is winning. Slowly, then all at once, the support is failing. The outer shells of the star, those layers where lighter elements are still happily fusing away, don't know anything is wrong. They're still producing energy, still radiating light into space. From the outside, the star looks exactly as it has for the past several million years. A bit bloated, certainly, red and cool at the surface, but stable, serene even. It's a bit like watching someone at a party who just received terrible news but hasn't processed it yet. They're still smiling, still making conversation, still going through the motions of normalcy. But inside, everything has changed. The foundation has cracked. The inevitable is approaching. In Buddhist philosophy, particularly in Tibetan traditions, there's a concept called bardo, an intermediate state between death and rebirth. It's described as a time of confusion and dissolution, where the structures that defined existence are breaking down, but the new form hasn't yet emerged. The consciousness is between states, neither fully one thing nor the other. Our star's core is in its own kind of bardo right now. It's no longer a functioning fusion reactor. That ended when iron became dominant, but it's not yet a neutron star or black hole. That comes later. It exists in this liminal space, this in-between time, where the old structures are dissolving but the new reality hasn't crystallized. 3 hours have passed since we started watching this morning. 3 hours of increasing crisis in the core. The temperature has reached its peak, the density continues to climb, and the pressure, the crucial pressure that holds everything up against gravity, is beginning its final descent. The iron tomb has been sealed. The star is entombed in its own success, imprisoned by the most stable element it could create. And now, like any tomb, it's becoming a place of dissolution and transformation. The next stage is approaching rapidly. The electron degeneracy pressure, that quantum mechanical barrier that has been holding up the core, is about to fail completely. When it does, when that last support gives way, the core will begin to collapse. Not slowly, not gradually, but catastrophically, falling inward on itself faster than the speed of sound, faster than anything has a right to fall. But we're not quite there yet. For now, in these final moments before noon on our cosmic clock, the iron core sits heavy and inert, its temperature still climbing uselessly, its pressure dropping inexorably, waiting. The tomb is quiet for now. It's noon now on our cosmic clock, and something is about to happen that has never happened before in this star's 20 million year lifetime. The iron core is going to fall. Not fall in the sense of tumbling through space. Fall inward, collapsing in on itself with a violence that defies description. In the next few seconds, something the size of Earth containing more mass than the Sun will compress down to the size of a city. The core will shrink by a factor of about 1,000 in diameter, which means its volume will decrease by a factor of 1 billion. Try to picture that for a moment. Imagine if Earth, all 12,000 kilometers of it, suddenly compressed down to about 12 kilometers across. Every mountain, every ocean, every continent, every bit of the planet's interior, all crushed into a sphere you could drive across in about 10 minutes if there were somehow a road on its surface. That's what's about to happen to our star's core, except it's going to happen in less time than it takes you to blink. The trigger is simple, almost anticlimactic given what follows. The electron degeneracy pressure, that quantum mechanical wall that's been holding the core up, finally gives way. The core has exceeded the Chandrasekhar limit. There's simply too much mass for the electrons to support, no matter how much they obey the Pauli exclusion principle. It's like that moment when you're stacking books on a shelf and you add just one too many. For a moment, nothing happens. The books teeter, they sway slightly, and then suddenly, catastrophically, the whole stack comes tumbling down. The collapse begins at the very center of the core and propagates outward at the speed of sound in the material, which at these densities is a significant fraction of the speed of light. Matter starts falling inward at velocities that reach 30,000 kilometers per second. To put that in perspective, that's 1/10 the speed of light. In a single second, material is falling inward, over a distance greater than Earth's diameter. If you were somehow riding along with this collapsing material, not that you could survive it even for a fraction of an instant, time would start behaving strangely. At 1/10 light speed, special relativity begins to matter. Time dilation becomes noticeable. Your watch would tick slightly slower than a watch held by someone far from the collapse. Though honestly, worrying about your watch in this situation would be like checking your email during an earthquake. As the core collapses, the density increases catastrophically. We started this morning at about 1 billion grams per cubic centimetre, which already seemed impossibly dense. Now we're climbing toward 100 trillion grams per cubic centimetre, then higher still. At these densities, atomic nuclei are no longer separated by electron clouds. They're touching each other directly. Think about that. In ordinary matter, atoms are mostly empty space. The nucleus is tiny compared to the cloud of electrons around it. If an atomic nucleus were the size of a marble, the electron cloud would extend out about 1 kilometre in every direction. Almost all of the volume of normal matter is just emptiness, the spaces between things. But in the collapsing core, that space is being eliminated. The nuclei are being pressed together until they touch, like marbles being poured into a jar and shaken until they settle into the tightest possible packing. Except these marbles are made of nuclear matter, and they really don't want to be this close together. Nuclear matter, the stuff that protons and neutrons are made of, has a remarkable property. It's extremely resistant to further compression. You can squeeze it somewhat, but once the nuclei are touching, trying to compress it further is like trying to compress a block of steel. You might deform it slightly, but you're not going to make much progress. This resistance comes from the strong nuclear force, the fundamental force that holds atomic nuclei together. At very short distances, the strong force becomes repulsive rather than attractive. It's nature's way of saying this close and no closer. The strong force is, well, strong. It's about 100 times stronger than the electromagnetic force and immensely stronger than gravity. But gravity doesn't care. Gravity is patient, and right now, gravity has 1.4 solar masses of material, all trying to occupy the same space. The strong force pushes back, but gravity just keeps squeezing. The density climbs higher. We're approaching something called nuclear density, the density at which matter becomes essentially one giant atomic nucleus. At this density, you can't really distinguish individual protons and neutrons anymore. They're all touching, all in contact, forming a kind of nuclear fluid. And then suddenly the collapse stops. Not slowly, not gradually. The infalling material hits nuclear density, and the resistance becomes so strong that the collapse halts almost instantaneously. Material that was falling inward at 30,000 kilometers per second suddenly encounters an immovable wall and bounces back. It's the rebound of all rebounds. Imagine throwing a super ball at the ground as hard as you can and watching it bounce back. Now multiply that by about 1 billion billion. The material rebounds with such violence that it creates a shockwave, a wall of compressed matter moving outward through the star. This is the core bounce, the moment when collapse transforms into explosion. The very center of the star, compressed to the point where matter itself pushes back, rebounds outward, and sends a pressure wave racing through the overlying material. The newly formed core at the center, compressed to nuclear density and about 10 to 20 kilometers across, is no longer made of iron. It's not made of atoms at all, really. It's made of neutrons, packed together so tightly that the entire core is essentially one gigantic atomic nucleus containing more particles than there are cells in every human who has ever lived. This is a neutron star in its first moments of existence, or rather, it's a proto-neutron star, still hot and roiling from the violence of its birth. Over the next few seconds it will settle into a slightly less chaotic state, though less chaotic is relative when you're talking about something with the mass of the Sun compressed into the size of Manhattan. But the neutron star, remarkable as it is almost a side story at this point. The main event is the shockwave racing outward through the overlying material. In Hindu cosmology, there's the concept of the cosmic dissolution, the pralaya. when the universe contracts back into undifferentiated potential before the next cycle of creation. The god Vishnu sleeps on the cosmic ocean, and all of manifest reality dissolves back into Brahman, the ultimate reality from which everything emerges. Our core collapse is its own kind of pralaya. Structure dissolves, individual identity disappears, everything collapses back into a kind of fundamental unity. The iron, the silicon, the oxygen, all the carefully constructed elements built up over millions of years, all compressed down into undifferentiated neutron matter. It's a return to a more fundamental state, a cosmic reset. The ancient Greeks had their own version in the myth of the Titans versus the Olympians. The Titans, the old gods, were overthrown and imprisoned in Tartarus, the deepest part of the underworld. The battle involved the very foundations of the cosmos shaking, mountains toppling, the earth splitting open. Gravity's ultimate victory over the star's structure echoes these mythic battles, a war between fundamental forces ending in imprisonment and transformation. The Aztecs believed we live in the age of the fifth sun, and that the previous four worlds had been destroyed by different catastrophes. The first by jaguars, the second by wind, the third by fire, the fourth by flood. Each ending was violent, complete, and made way for the new world to emerge from the ashes of the old. Our collapsing core is experiencing its own catastrophic ending. The structure that defined it, the carefully layered shells of different elements, the stable configurations of nuclei and electrons, all of it is being destroyed in a matter of seconds. But like the Aztec worlds, this destruction is making way for something new. There's a particular moment during the collapse that's worth contemplating, though it lasts for only a fraction of a second. It's the moment when the density is high enough that neutronization happens rapidly, when protons and electrons are being forced together to form neutrons throughout the collapsing material. Each neutronization releases a neutrino, and in this brief moment, as a solar mass of material undergoes this transformation, the number of neutrinos being produced is almost incomprehensible. We're talking about 10 to the 58th power neutrinos. That's a 1 followed by 58 zeros. For comparison, the number of atoms in the entire Earth is only about 10 to the 51st power. These neutrinos carry away an enormous amount of energy. In fact, they carry away about 99% of the energy released by the core collapse. Only about 1% goes into the shockwave that will eventually blow the star apart. The rest, that vast flood of ghostly particles, just streams out into space at the speed of light. If you were observing this star from a nearby planet, say 10 light-years away, you wouldn't see anything unusual yet. The light from the explosion hasn't reached the surface, but the neutrinos, racing outward at light speed, have already left the star and are spreading through space in an ever-expanding sphere. About 3 hours before you saw the star brighten in a spectacular supernova, your neutrino detector, if you had one, would register a brief, intense burst. Billions of neutrinos would pass through the detector in just a few seconds. Most would pass through without interacting, as neutrinos do, but a few, a tiny fraction, would leave a signal. This actually happened in 1987 when a star exploded in the Large Magellanic Cloud, a small galaxy near our Milky Way. Neutrino detectors on Earth recorded a burst of neutrinos about 3 hours before the star became visibly brighter. It was the first time in human history that we detected neutrinos from a supernova, and it confirmed our theoretical understanding of stellar collapse. The Norse had a myth about Ragnarok, the twilight of the gods, when the world serpent Jörmungandr would thrash and writhe, causing the earth to shake and the seas to rise. The wolf Fenrir would break free from his chains, the sun and moon would be devoured, the entire world would convulse in the final battle between gods and giants. There's something of Jörmungandr's thrashing in the core collapse. The star's foundation is shaking. The carefully maintained equilibrium between gravity and pressure is breaking, and the forces involved are so extreme that the very structure of matter is being rearranged. It's a cosmic battle, though one played out in physics rather than mythology. In Japanese Shinto tradition, the world is understood as a fragile balance. The kami, the spirits that inhabit all things, maintain order through their relationships and interactions, but this order is always threatened, always precarious. Earthquakes, tsunamis, volcanic eruptions all remind us that the ground beneath our feet is not as solid as it seems. The star's iron core thought it had reached stability, a steady state where electron degeneracy pressure perfectly balanced gravity's squeeze. But that stability was an illusion, or at least a temporary state. The true nature of the system, the ultimate victory of gravity over stellar structure, was always lurking beneath the surface. The shockwave is propagating outward now, moving through the infalling material like a wave moving through water. But here's where things get complicated. The shockwave is travelling outward, but it's also losing energy as it goes. Remember all those layers of the star above the core? The silicon shell, the oxygen shell, the neon, the carbon, the helium, the hydrogen. All of that material is still falling inward, still being pulled down by gravity. The shockwave has to push through all of that infalling material, and every bit of material it encounters robs it of energy. It's like trying to run up a downward moving escalator. You can make progress, but it's exhausting, and if you slow down even a little, you'll start being carried backward. For a while, it looks like the shockwave might stall. It might run out of energy before it reaches the surface. If that happened, the explosion would fail, and the entire star would just collapse down into the neutron star or black hole without any visible supernova at all. These are called failed supernova, and astronomers have actually observed them. A massive star is there one day, and the next day it's just gone, vanished without the expected brilliant explosion. But our star is going to explode. Something is going to help the shockwave, give it the extra push it needs to keep going, and that something involves those neutrinos we mentioned earlier. Even though neutrinos barely interact with matter, when you have 10 to the 58th power of them streaming outward through the star, barely becomes occasionally. A tiny fraction of the neutrinos, perhaps 1 in a trillion, interacts with the infalling material. Each interaction deposits a bit of energy. 1 in a trillion sounds like nothing, but when you have that many neutrinos, even this tiny fraction adds up to a significant energy transfer. It's like a crowd of people, each tossing a single pebble at a boulder. Any individual pebble bounces off harmlessly, but millions of pebbles, millions of tiny impacts, can actually move the boulder. The neutrinos heat the material behind the shockwave, giving it extra energy, helping to drive it outward. This mechanism, called neutrino heating, is one of the key processes that allows the shockwave to succeed in blowing the star apart. Buddhist philosophy speaks of interdependence, the concept that all things arise together in mutual causation. Nothing exists in isolation. Everything affects everything else in an endless web of relationships. The collapsing core creates neutrinos. The neutrinos heat the outer layers. The heated layers drive the shockwave. The shockwave will eventually expel material that will enrich the interstellar medium, which will form new stars, which will one day collapse and create more neutrinos. The cycle continues, everything connected, everything influencing everything else. 6 hours have passed now on our cosmic clock since we began watching this morning. 6 hours since the silicon burning was in full swing, and in those 6 hours, particularly in the last few minutes, the star has experienced more violence, more extreme conditions than in all the previous 20 million years combined. The core has collapsed from something the size of Earth to something the size of a city. The density has increased by a factor of 100 trillion. Material has fallen inward at 1/10 the speed of light, and then rebounded with comparable violence. Neutrinos beyond counting have been created and have fled into space. A shockwave has formed and is now battling its way outward through the star. And through all of this, the outer layers of the star, the visible surface that anyone observing from outside would see, still looks completely normal. The photosphere is still glowing with the same dull red light it's had for the past few million years. No hint of the catastrophe unfolding in the core has reached the surface yet. It's a bit like watching a building whose foundation has just collapsed but whose upper floors haven't received the news yet. The penthouse is still intact. People are still going about their business, completely unaware that in a few seconds the entire structure is going to come crashing down. The Aboriginal peoples of Australia have stories from the Dreamtime about the world being created and recreated through the actions of ancestral beings. These beings would travel across the land, and their actions, their journeys, their battles and love affairs would shape the landscape. Mountains would rise where they fought, rivers would flow where they danced, and all of creation would bear the marks of their passage. In a sense, the collapsing core is reshaping reality itself, not the landscape of Earth, but the fundamental nature of matter. Protons are becoming neutrons, electrons are disappearing, the very structure of the periodic table is being rewritten. When this is over, when the dust settles, figuratively speaking, the core will be something unprecedented, matter in a state that exists nowhere else in the universe except in the hearts of neutron stars. There's also something profound in the timescales involved. The star spent 20 million years carefully building up its elements, fusing hydrogen into helium, helium into carbon, carbon into oxygen, all the way up to iron. 20 million years of patient construction. And then, in less than a second, all of that careful work is undone. The iron photodisintegrates back into lighter elements. The silicon, oxygen, carbon, all of it gets crushed down into neutron matter. 20 million years erased in less time than a human heartbeat. It's a reminder that destruction is often faster than creation. You can spend years building a sandcastle and a single wave can wash it away in seconds. The universe operates on the same principle, just with more impressive numbers. The shockwave is still pushing outward, still fighting against the infalling material, still being heated by those trillions upon trillions of passing neutrinos. It hasn't reached the outer layers yet. That comes next. For now, in this strange interval between collapse and explosion, the star exists in a state of quantum uncertainty, poised between being and not being. The core has collapsed, but the star hasn't exploded. The neutron star has formed, but it's still hidden beneath layers of stellar material. The end has begun, but it hasn't finished. In Tibetan Buddhist meditation practices, there's a moment between thoughts, a gap in the constant stream of mental chatter. In that gap, practitioners say, you can glimpse the nature of mind itself, pure awareness before it crystallizes into specific thoughts or feelings. It's fleeting, lasting only as long as it takes for the next thought to arise. But in that brief space exists something fundamental. Our star is in its own gap between thoughts right now. The old structure, the carefully layered shells of fusing elements, is gone. The new structure, whatever emerges from this collapse, hasn't fully formed yet. In this in-between space, this bardo, the star is purely potential, ready to transform into something entirely new. The collapse is complete. Gravity has won its ancient battle. The core has been compressed beyond anything that seemed possible just hours ago. But gravity's victory isn't the end of the story. It's barely the beginning. The shockwave is still climbing, still pushing outward, carrying with it the energy of collapse transformed into the energy of explosion. And in a few hours, when it reaches the surface, the universe is going to witness one of its most spectacular displays. The tomb has collapsed. Now comes the resurrection. It's 6 in the evening now on our cosmic clock, and the shockwave has been climbing outward through the star for hours. It started at the collapsed core, that newly formed neutron star sitting at the centre like an impossibly dense pit. And now it's pushing through the layers of the star, heating everything it touches to temperatures that make the original core burning seem almost cool by comparison. We're talking about temperatures of 100 billion degrees Kelvin. That's 10 times hotter than the core temperature during silicon burning this morning. At these temperatures, thermal energy alone is enough to break apart atomic nuclei. Iron nuclei that survived the morning are now being torn back into their constituent parts, ripped apart by the sheer violence of the thermal motion. But here's where something beautiful happens, something that's been impossible up until this moment. The shockwave isn't just destroying nuclei, it's creating them too. And not just any nuclei, it's forging the heaviest elements in the periodic table, the ones that couldn't form through any normal stellar process. Let's talk about gold for a moment. Gold, that lustrous yellow metal that humans have valued for thousands of years. You can't make gold during normal stellar fusion. You just can't. Even in the hottest cores of the most massive stars, even during the desperate final hours of silicon burning, gold doesn't form. It requires something more extreme. The reason has to do with nuclear structure. To make gold, you need to build up a nucleus containing 79 protons. That's a lot of protons, and they really don't want to be together. Protons all have positive charge, and positive charges repel each other. The more protons you try to pack into a nucleus, the harder it becomes. You need neutrons to act as nuclear glue, and you need just the right conditions to add those neutrons faster than the nucleus can fall apart. In the shockwave, you have those conditions. The temperature is enormous, providing the energy needed to overcome the electrical repulsion between protons. The density is still quite high, meaning particles are constantly colliding. And most importantly, you have an absolutely enormous flux of neutrons. Remember all those protons that got crushed together with electrons to form neutrons during the collapse? Well, not all of those neutrons ended up in the neutron star. Some are still mixed in with the material being swept up by the shockwave. And these free neutrons, having no electrical charge, can easily crash into atomic nuclei without being repelled. This is called the R process, where R stands for rapid. Rapid neutron capture. A nucleus, say iron 56, gets hit by a neutron and becomes iron 57. Before it can decay, another neutron hits it, making iron 58. Then another, and another, and another. The nucleus is absorbing neutrons faster than it can shed them through radioactive decay. This rapid accumulation of neutrons creates nuclei that are incredibly neutron-rich, far more so than anything you'd find in nature under normal circumstances. These neutron-rich nuclei are unstable. They want to convert some of those extra neutrons back into protons through beta decay. And when they do, when a neutron splits into a proton, an electron, and a neutrino, the element changes. Iron becomes cobalt, cobalt becomes nickel, nickel becomes copper. Step by step, the periodic table builds upward. Given enough neutrons and enough time, you can build all the way up to the heaviest elements: gold, platinum, uranium, thorium. Every atom of gold in every ring, every necklace, every gold bar in every vault was created in moments like this, in the shockwave of a dying star, in conditions of such extreme heat and pressure that matter itself was being reshaped. The wedding ring on someone's finger, if they're wearing one, contains atoms that were forged in a stellar explosion that happened before our solar system even existed. Those gold atoms have been on a journey spanning billions of years, from the heart of a dying star to a nebula, to the protoplanetary disk that formed our sun and planets, to Earth's crust, to a mine, to a jeweler, to a finger. Every single heavy element you can think of, anything heavier than iron, was created in one of two ways. Either in the slow neutron capture process that happens in the extended envelopes of red giant stars over thousands of years, or in the rapid neutron capture process that happens in supernova shockwaves over seconds. Most of the really heavy stuff, the gold and platinum and uranium, comes from supernovae. There's another process happening in the shockwave too, something called the alpha-rich freeze-out. In the hottest, densest regions just behind the shockwave front, matter exists in a kind of nuclear equilibrium. Nuclei are constantly being broken apart by high-energy photons and constantly being reassembled by collisions. It's a furious dance of creation and destruction, happening trillions of times per second. As the material expands and cools slightly, this equilibrium freezes out, and whatever nuclei happen to be stable at that temperature get locked in. The exact mix of elements depends on the temperature, density, and the ratio of protons to neutrons, but under the right conditions, this process creates specific isotopes of elements like titanium-44, chromium-48, and nickel-56. Nickel-56 is particularly important. It's radioactive with a half-life of about 6 days. It decays into cobalt-56, which then decays into iron-56. And each decay releases energy in the form of gamma rays. This radioactive decay is actually what powers the visible light from supernovae weeks and months after the initial explosion. The shockwave gets things started, but the radioactive glow of decaying nickel and cobalt keeps the show going. It's worth pausing to appreciate the efficiency of all this. The star spent 20 million years carefully building up elements through fusion, releasing energy slowly and steadily. Now, in a matter of seconds, it's creating elements that fusion could never make, powered by the gravitational energy released during the core collapse. Gravity, patient and implacable, has stored energy over those 20 million years by holding the star up against its own weight. And now all that stored energy is being released at once, like a spring that's been compressed for eons suddenly snapping back. The mythology of the divine smithy appears in cultures across the world, and it's easy to see why. There's something primal about the image of a god working at a forge, hammering raw material into something refined and useful, the sparks flying, the heat radiating, the transformation of base matter into something valuable. The Greek god Hephaestus, lame but incredibly skilled, forging weapons and armour for the gods in his workshop beneath Mount Etna. The Norse god Wayland the smith, who could craft anything with his hands, creating swords of legendary sharpness. The African Orisha Ogun, master of iron and technology, the force of transformation through fire and metal. These myths weren't trying to describe nuclear physics, obviously, but they captured something true about the universe. Creation requires extreme conditions. Transformation requires heat and pressure. The most valuable things are forged in fire. Our shockwave is the ultimate smithy, working not with iron and steel, but with atomic nuclei, not with hammers and anvils, but with neutrons and gamma rays, and it's creating not weapons or tools, but the raw materials from which everything else is made, the gold and platinum in our electronics, the uranium that powers nuclear reactors, the rare earth elements in our smartphones, all forged here in the cosmic smithy of stellar death. In Hindu mythology, Agni is the god of fire, not just physical fire, but the transformative fire that underlies all change. Agni is present in the hearth, in the lightning, in the sun, in the cremation pyre. He's the force that transforms, that breaks down the old and creates the new. The Vedic hymns describe Agni as having 7 tongues, 7 flames, each consuming a different aspect of reality. The shockwave has its own 7 tongues, its own transformative fires. Photodisintegration, breaking apart old nuclei. Neutron capture, building up new ones. Beta decay, converting neutron-rich nuclei into new elements. Alpha particle interactions, creating intermediate mass elements. Nuclear statistical equilibrium, establishing elemental abundances. Each process a different tongue of flame, each consuming and creating simultaneously. The Celtic goddess Brigid holds a similar role in Irish mythology. She's associated with smithcraft, yes, but also with poetry and healing. The forge, the bardic arts, and medicine were all understood as aspects of the same transformative power. You heat metal to shape it. You heat words in the mind to shape them. You apply heat through fever to heal the body. Transformation through fire is the unifying principle. And there's something poetic in the literal sense about what's happening in the shockwave. The star is composing its own epic, writing its autobiography in the nuclei it creates. Future astronomers will study the light from this supernova and read the spectral lines like poetry, each wavelength telling a story about temperature, density, composition. The star is speaking, and its words are written in the language of nuclear physics. The Japanese tradition of sword-making, particularly the forging of katanas, was understood as a spiritual practice as much as a craft. The smith would purify himself before beginning, would pray to the kami, the spirits, asking for guidance. The folding and hammering of the steel, done dozens of times, was a meditation, a way of putting one's spirit into the blade. There's no consciousness in the shockwave, no intentionality. But there is a kind of inevitability to the process, a rightness to the physics playing out. The universe has rules, and those rules followed faithfully lead to this: heavy elements, complex chemistry, the possibility of planets and life and consciousness. The star is unknowingly creating the conditions for minds to eventually emerge that will look back and understand what happened here. The shockwave has now travelled through several layers of the star. It's heated the silicon shell, causing explosive silicon burning that adds to the shockwave's energy. It's passed through the oxygen shell, the neon shell, the carbon shell. Each layer briefly ignites in a final burst of fusion as the shockwave sweeps through, adding its energy to the outward push. Think of the shockwave as a wave moving through a stadium during a sports game. Each row of people stands up, throws their arms in the air and sits back down. The wave moves, but the people don't. Each section participates for a moment and then returns to rest. Except in our stellar stadium, when each section participates, it undergoes nuclear fusion, creates new elements and gets blasted into space. So it's a bit more dramatic than a typical wave at a ballpark. Though honestly, given how excited some sports fans get, the energy levels might not be that different. The material just behind the shockwave front is a nuclear physicist's dream laboratory. Conditions exist there that we can't replicate on Earth, not even in our largest particle accelerators. The temperatures, the densities, the particle fluxes, all of it is beyond our current technology. We can simulate it in computers. We can calculate what should happen using our understanding of nuclear physics, but we can't recreate it experimentally. This is why studying supernova is so important. They're natural experiments in extreme nuclear physics, testing our theories under conditions we could never produce artificially. When we observe a supernova, measure its light curve, study its spectrum, we're reading the results of experiments conducted in nature's laboratory. And so far, our theories have held up remarkably well. The shockwave is also creating complex nuclear burning patterns through something called Rayleigh-Taylor instabilities. Imagine pouring honey into water. The honey is denser than the water, so it should sink. But it doesn't sink smoothly. It forms these beautiful mushroom-shaped plumes, fingers of honey extending down into the water, while fingers of water extend up into the honey. These are Rayleigh-Taylor instabilities, the result of a denser fluid trying to move through a less dense fluid. In the shockwave, you have hot material trying to rise through cooler material, and dense material trying to sink through lighter material. The result is turbulent mixing, with plumes and fingers extending in all directions. This mixing is actually crucial for the supernova. It brings heavy elements from the core up to higher layers, where they can eventually be expelled into space. Without this mixing, much of the material forged in the shockwave would fall back onto the neutron star and be lost. The turbulence creates another beautiful effect. It allows for local variations in temperature, density, and composition. In one region, conditions might favor the creation of gold. A few kilometers away, platinum might be preferentially produced. This patchwork of slightly different conditions leads to a variety of elements being created, ensuring that the periodic table gets well represented in the final explosion. Aboriginal firestick farming in Australia provides an interesting parallel. Indigenous Australians would deliberately burn sections of land, creating a mosaic of different vegetation stages. Some areas freshly burned, some regrowing, some mature. This diversity of habitats supported a greater variety of plants and animals than a uniform landscape would. The turbulent shockwave creates a similar mosaic, a patchwork of different nuclear burning conditions that supports a greater diversity of elements than uniform conditions would produce. Destruction enabling diversity, death creating the conditions for future life. 3 hours have passed since the core collapsed at noon. 3 hours of the shockwave climbing outward, heating material, creating elements, mixing heavy nuclei with lighter ones. The shockwave has travelled from the centre of the star, where the neutron star now sits in its compressed glory, outward through thousands of kilometres of stellar material. It hasn't reached the surface yet. That's still hours away, but it's making progress, pushing steadily outward, powered by the energy of collapse and fed by neutrino heating from below. The silicon that was burning this morning is now completely processed. Some of it is in the neutron star, crushed beyond recognition. Some of it has been fused into heavier elements in the early stages of the collapse, and some of it is now being swept up by the shockwave, heated to extremes, and transformed into a zoo of different nuclei. The oxygen shell above the silicon has experienced its own rapid burning as the shockwave passed through. Oxygen nuclei fused together in a desperate final burst of fusion before being torn apart by the heat and then reassembled into different configurations by the rapid nuclear processes in the shockwave. Layer by layer, the shockwave is working its way upward, like someone climbing a ladder. Each rung reached opens up new regions of the star to its transformative effects. Each layer adds its own contribution to the mix of elements being created. The philosopher's stone, that mythical substance the alchemists sought, was supposed to be able to transmute any metal into gold. They never found it because it doesn't exist, at least not as a substance you could hold in your hand. But the shockwave is the real philosopher's stone. It's transmuting everything it touches, turning silicon into gold, iron into platinum, nickel into elements that don't even have stable isotopes. It's the ultimate alchemical tool, and it's powered not by mystical forces, but by gravity, nuclear physics, and the energy stored in 20 million years of stellar evolution. The Shockwave is the fire that transforms. It's Hephaestus's forge, Agni's 7 tongues, Brigid's flame. It's the cremation pyre and the smithy and the transformative heat of fever all at once. And it's writing a story in atomic nuclei, a story that will eventually be read by creatures made from earlier chapters of that same story. The forge is awake, the elements are being born, and the Shockwave climbs onward, carrying its nuclear fire toward the surface, where the real show is about to begin. It's 9 in the evening now, and the Shockwave has been climbing for 9 hours. 9 hours might not sound like much when we're talking about a star that lived for 20 million years, but in those 9 hours, this wave of superheated matter has travelled through most of the star's radius, transforming everything it touches. The Shockwave is moving fast, anywhere from 3,000 to 30,000 kilometers per second, depending on which layer it's passing through. To put that in perspective, at its slower pace, it could cross the entire United States in about 1 second. At its faster pace, it's moving at a significant fraction of the speed of light, fast enough that if you were somehow watching it approach, you'd barely have time to process the information before it reached you. Not that you could watch it, of course. The Shockwave is buried deep inside the star, hidden beneath layers of hydrogen and helium that are still glowing with their normal, boring pre-explosion light. From outside, the star still looks completely unremarkable. A large red supergiant, perhaps a bit variable in its brightness as these old stars often are, but nothing to suggest the violence unfolding in its interior. It's like watching a building from the outside while an earthquake is happening inside. The exterior looks calm, maybe a few windows rattling, but you have no idea that inside the walls are cracking, the foundation is shifting, and everything is about to come tumbling down. The Shockwave has now reached the helium shell, a thick layer of helium that surrounds the core like an onion layer. This helium has been sitting here for millions of years, waiting patiently for its turn to fuse. Under normal circumstances, it would have eventually been pulled into the core region as the star aged, where it would undergo helium burning to create carbon and oxygen. But these are not normal circumstances. The Shockwave arrives and suddenly the helium shell is heated to billions of degrees in a matter of seconds. The helium doesn't gradually begin fusing. It explodes into fusion all at once in what's called explosive helium burning. Imagine a forest that's been dry for years, full of dead wood and tinder. A normal fire would spread gradually, taking hours or days to consume the forest. Now imagine someone simultaneously igniting every tree at once. That's explosive helium burning. The entire shell undergoes fusion essentially simultaneously, releasing an enormous amount of energy in a tiny fraction of the time it would normally take. This explosive burning adds to the Shockwave's energy, giving it a boost. It's like a runner getting a burst of energy from the crowd cheering them on, except the crowd is nuclear fusion, and the energy boost is enough to vaporize a planet. The helium fuses into carbon, oxygen, and a bit of neon. These newly created elements are immediately mixed into the turbulent flow behind the Shockwave. Heavy elements from the core, created during the collapse and in the Shockwave itself, are mixing with lighter elements from the outer shells. It's all getting thoroughly scrambled, like someone vigorously stirring a cosmic soup. This mixing is actually one of the most important aspects of the supernova for the universe at large. If the layers remained perfectly separated, if heavy elements stayed deep in the star and light elements stayed on the outside, then when the star exploded, we'd end up with a supernova remnant that was chemically segregated. Heavy stuff in one place, light stuff in another. but the turbulent mixing ensures that when the star finally blows apart, the ejected material will contain a good mix of elements. Heavy nuclei from the core will be thoroughly blended with hydrogen and helium from the envelope. This mixed material will eventually be incorporated into new stars and planets, giving them the chemical diversity they need for interesting things to happen. Without this mixing, planets like Earth couldn't exist. You need heavy elements to make rock. You need oxygen for water. You need carbon for organic chemistry. And you need these elements mixed together with hydrogen and helium so that the right combinations can form. The turbulent shockwave is providing the stirring mechanism that makes future complexity possible. In mythology, there are countless stories of heroes journeying through the underworld, descending through layers of reality to reach some ultimate truth, or to rescue someone from the land of the dead. The Greek hero Orpheus descended into Hades to retrieve his wife Eurydice. The Sumerian goddess Inanna passed through 7 gates, removing an article of clothing at each one, until she stood naked before the queen of the underworld. Dante's Divine Comedy describes a descent through 9 circles of hell, each one darker and more terrible than the last, before emerging on the other side to begin the ascent through purgatory and paradise. Our shockwave is making its own journey through the layers of the star, though it's moving upward rather than downward. Each layer it passes through is a different world with different conditions, different densities, different compositions. The silicon shell was one world, the oxygen shell another, the neon shell a third, and now the helium shell represents yet another distinct realm in this stellar architecture. But unlike the mythic heroes who journey alone, our shockwave is transforming everything it encounters. Orpheus passed through the underworld without changing it. Inanna stripped herself bare, but left the realm of the dead unchanged. Dante observed the circles of hell, but didn't alter them. The shockwave, though, is remaking reality as it goes, turning the underworld of the star's interior into something entirely new. The Egyptian concept of the soul's journey through the duat, the underworld, involved passing through 12 gates, one for each hour of the night. At each gate, the soul had to recite the correct passwords and spells, had to demonstrate knowledge of the realm's mysteries. The journey was perilous, full of monsters and obstacles, but those who successfully navigated it would be reborn with the morning sun. The shockwave's journey has its own gates, its own hours. Each shell it encounters presents different challenges. The silicon shell with its desperate final burning, the oxygen shell with its own explosive fusion, the neon shell, the carbon shell, each one a barrier to overcome, each one adding or subtracting energy from the shockwave. And like the Egyptian soul, the shockwave is heading toward a rebirth of sorts, not of the star itself, which is dying, but of the matter that composed it. When the shockwave finally breaks through the surface, the star's material will be reborn, scattered into space to begin new adventures in new configurations. Hindu philosophy speaks of the chakras, wheels or centers of energy that run along the spine from the base to the crown of the head. Energy must flow through each chakra in turn, and blockages at any level can prevent spiritual development. The journey of consciousness is understood as an ascent through these layers, each one representing a different level of awareness. The star's layers are its own chakras in a sense, each one representing a different stage of its nuclear evolution. The iron core is the base, the foundation. The silicon shell above it, then oxygen, neon, carbon, helium, and finally the hydrogen envelope at the crown. The shockwave is energy moving through these layers, though whether it reaches the crown depends on whether it maintains enough strength to push through all the barriers. Native American vision quest traditions involve journeying away from the community, often to a mountain or isolated place, where through fasting and meditation one might receive visions or guidance from the spirit world. The journey involves trials, physical discomfort, and the stripping away of the ordinary self to reveal something deeper. The Shockwave is on its own vision quest, moving away from the community of the core, climbing toward the isolated heights of the star's outer envelope, being tested at each layer, losing and gaining energy, having its composition transformed by what it encounters. The Celtic tradition has many stories of journeys to the other world, which could be reached by going under the earth, across the sea, or through special portals like fairy mounds. Time worked differently in the other world. A person might spend what seemed like a day there and return to find that years or centuries had passed in the mortal world. In the Shockwave's journey, time is also behaving strangely, though for different reasons. To an outside observer watching the star, nothing appears to be happening. Time seems to crawl, but in the Shockwave itself, matter is being transformed on timescales of seconds. Nuclei are being created and destroyed, elements are mixing, temperatures are fluctuating wildly. Subjective time, if such a thing could be said to exist for a shockwave, is moving at a completely different pace than objective stellar time. The shockwave has now entered the hydrogen envelope, the outermost layer of the star. This is where most of the star's mass actually resides. The core and all those inner shells, despite their density and their importance, only contain a small fraction of the star's total material. The hydrogen envelope is vast, extending for hundreds of millions of kilometers from the core to the surface. This hydrogen has never undergone fusion. It's been sitting out here in the cool outer reaches of the star, far too cool and far too diffuse for nuclear reactions. It's pristine material, almost unchanged since the star first formed from a collapsing gas cloud 20 million years ago. Until now, the shockwave arrives, and suddenly this peaceful hydrogen is being heated to millions of degrees. Not hot enough for fusion, not in most of the envelope anyway, but hot enough to ionize completely. The electrons are stripped from the hydrogen nuclei, creating a plasma of free protons and electrons. This ionization requires energy, and that energy comes from the shockwave. It's like the shockwave is paying a toll to pass through each layer, and the hydrogen envelope is extracting its payment. The shockwave loses energy as it heats and ionizes this vast amount of material. This is one of the biggest challenges the shockwave faces. The hydrogen envelope is so massive and extends so far that heating it all takes an enormous amount of energy. If the shockwave started with just the energy from the core bounce, it would likely stall somewhere in the hydrogen envelope, having exhausted its energy before reaching the surface. But remember those neutrinos we talked about earlier? The ones streaming out from the cooling neutron star at the center. They're still providing energy, still heating the material behind the shockwave, still giving it the boost it needs to keep going. It's a bit like climbing a mountain. You start with a burst of energy from the bottom, but as you climb, you get tired. If you don't have some way to replenish your energy, snacks maybe, or the encouragement of fellow climbers, you might run out of strength before reaching the summit. The neutrinos are the shockwave snacks, the small but steady energy input that makes the difference between success and failure. Buddhist philosophy describes the bardo states, the intermediate stages between death and rebirth. The Tibetan Book of the Dead describes these states in detail, noting how consciousness experiences increasingly strange and terrifying visions as it moves through the dissolution of the elements. Earth dissolves into water, water into fire, fire into air, air into consciousness. Each dissolution is accompanied by specific visions and sensations. The shockwave is experiencing its own dissolution and transformation as it moves through the star. The neat layered structure of shells is dissolving into turbulent mixing. elements are being created and destroyed. The boundary between the shockwave and the material ahead of it becomes fuzzy, smeared out by turbulent eddies and instabilities. The star's internal architecture is dissolving, preparing for the rebirth that will scatter its substance across light years of space. Convection currents have started in the hydrogen envelope, driven by the heat from below. Hot material rises, cool material sinks, creating vast circulation patterns. If you could somehow see inside the star at this moment, you'd see enormous plumes of hot plasma rising through cooler material, like lava lamps the size of Jupiter. These convection patterns help carry energy from the shockwave outward, but they also create complex flow patterns that affect how the supernova will eventually look. When the light finally breaks through the surface, the details of its spectrum and its brightness will carry information about these convection patterns, about the turbulent mixing, about all the complex fluid dynamics happening in the star's interior. The shockwave is now perhaps halfway through the hydrogen envelope. It's been weakened by all the energy it's expended heating material, but it's still moving, still pushing outward. The neutrinos continue their steady contribution, and the shockwave continues its climb. An hour and a half have passed since we started watching at 9 in the evening. An hour and a half of the shockwave working its way through the hydrogen envelope, heating millions of solar masses of material, creating convection patterns, mixing elements together. The surface is getting closer. Not close, not yet, but closer. The shockwave has travelled through the star's core, through the silicon shell, the oxygen, neon, carbon and helium shells, and now through much of the hydrogen envelope. One more push, one more stretch of this cosmic journey, and it will break through. The star still looks normal from outside. The photosphere, the visible surface, is still glowing with its usual dull red light. But beneath that calm exterior, the interior is in chaos. The carefully structured layers are gone, replaced by turbulent mixing and convection. The core has collapsed to a neutron star. Heavy elements are being carried outward, and a shockwave of unimaginable energy is climbing toward the surface. The building hasn't fallen yet, but the foundation has collapsed. The walls are cracking, and the structural integrity is about zero. Any moment now, the exterior is going to catch up with what the interior already knows. The journey through the layers is nearly complete. The gates have been passed, the chakras traversed, the vision quest approaching its climax. The shockwave carries with it the transformed substance of the star, the newly forged elements, the mixed material that will seed future star formation. And soon, very soon, it will break through into the light, and the universe will witness what happens when stellar death becomes stellar revelation. The surface awaits, the final barrier, the last gate before rebirth. And the shockwave climbs on, patient and inexorable, carrying its nuclear fire toward the stars. It's 10:30 in the evening, and after hours of climbing through the star's interior, the shockwave has finally reached the photosphere. The photosphere is the visible surface of the star, the layer where photons can finally escape into space after spending thousands of years bouncing around in the stellar interior. It's what we see when we look at any star, including our sun. The outer boundary, the edge. And now, the shockwave is about to break through it. The photosphere itself is surprisingly thin, just a few hundred kilometers deep. That might sound like a lot, but remember we're talking about a star that extends for hundreds of millions of kilometers from its core. The photosphere is like the skin on an apple, a thin boundary layer between the star's interior and the vast emptiness of space. Under normal circumstances, the photosphere is a relatively calm place. Photons that have been created deep in the star's core finally make it to this layer and escape, carrying energy away. The temperature here is only a few thousand degrees, cool enough that atoms can hold on to some of their electrons. It's almost peaceful compared to the nuclear inferno deeper in. But these are not normal circumstances. The shockwave, carrying temperatures of millions of degrees, is about to hit this thin, relatively cool layer like a freight train. What happens next occurs very quickly, at least from an outside perspective. The shockwave reaches the photosphere, and suddenly the material there becomes transparent. The dense, opaque layers that have been trapping light inside the star for its entire life suddenly turn into something that light can pass through freely. It's like someone suddenly removed a lampshade. For 20 million years, this star has had a covering over its nuclear furnace, keeping most of the light trapped inside, letting only a measured amount escape. And now, in a matter of minutes, that covering is torn away. The first photons from the shockwave itself break free and race into space at the speed of light. These are high-energy photons, gamma rays and X-rays, carrying the story of the violence happening in the star's interior. They zip past any nearby planets, past any unfortunate spaceships that might be in the area, and head out into the galaxy. If you were an astronomer on a planet a few hundred light years away, watching this star through a telescope, this would be the moment you've been waiting for without knowing it. For years, maybe for your entire career, this star has been just another red supergiant, catalogued and occasionally observed, but not particularly interesting. And then, over the course of a few hours, it begins to brighten. Not slowly, not gradually, like variable stars often do, but rapidly, dramatically. In the span of a day, this star goes from being barely visible to being one of the brightest objects in your night sky. Within a week, it might be bright enough to cast shadows. In a month, it could rival your planet's moon in brightness. This is a supernova, the light from stellar death finally breaking free, announcing to the universe that a star has died and is giving back everything it created during its lifetime. The luminosity at peak is staggering. A single supernova can briefly outshine an entire galaxy. Think about that. A galaxy contains hundreds of billions of stars, each one shining with its own light. And this one exploding star for a few weeks puts out more light than all of them combined. If you could convert that to something more tangible, a supernova at peak brightness is emitting about 5 billion times more light than our Sun. If our Sun suddenly became a supernova at this brightness, and you were standing on Earth, well, you wouldn't be standing for long. The intensity of the light would be enough to vaporize the planet's surface in seconds. Fortunately, supernovae are quite far away from us. The nearest star that might become a supernova in the foreseeable future, Betelgeuse, is about 650 light-years distant. If it exploded tomorrow, it would indeed become very bright in our night sky, perhaps bright enough to read by, but it wouldn't cause any damage. We'd just get a spectacular light show. The spectrum of the light is particularly interesting. As the photosphere expands and cools, different elements announce their presence through their characteristic spectral lines. Hydrogen shows up, of course. Helium appears, but also calcium, iron, silicon, oxygen. Each element leaves its fingerprint on the light, telling astronomers what's happening inside the expanding shell. Some of the light comes from the shockwave itself, the thermal radiation from matter heated to millions of degrees, but much of it, particularly as weeks go by, comes from radioactive decay. Remember all that nickel-56 we talked about being created in the shockwave? It's decaying now, first into cobalt-56, then into iron-56, and each decay releases gamma rays. These gamma rays get absorbed by the expanding material and re-emitted as visible light. It's like the supernova has its own internal power source, keeping it bright for months even as it expands and cools. The radioactive glow of nickel and cobalt decay is what powers the supernova's extended light curve. Birth of light from darkness is one of the most universal themes in human mythology. Almost every culture has a creation story that involves light emerging from primordial darkness, order arising from chaos. In Hindu tradition, there's the festival of Diwali, the festival of lights. It celebrates the victory of light over darkness, knowledge over ignorance, good over evil. Lamps are lit, fireworks are set off, and the darkness is pushed back by the accumulated light of millions of small flames. A supernova is the ultimate Diwali celebration, a cosmic festival of lights that pushes back the darkness across hundreds of light years. The Christian tradition speaks of resurrection, of light emerging from the darkness of death. The Easter story centers on this transformation, death overcome by new life, the tomb found empty on the third day, darkness giving way to dawn. Our star's light breaking through the photosphere is its own resurrection story. Not the star itself being resurrected, that's gone, collapsed down to a neutron star or black hole. But the light, the energy, the very substance of the star being reborn, scattered into space to begin new journeys. In Zoroastrian belief, Ahura Mazda is the uncreated light, the source of all goodness and truth, locked in eternal battle with Angra Mainyu, the spirit of darkness and chaos. Light and darkness are fundamental forces, and the universe is the battleground where this cosmic struggle plays out. The supernova is light winning a battle in this cosmic war. Darkness had imprisoned the star's light for 20 million years, keeping it trapped inside layers of dense matter. But now, through the violence of collapse and explosion, the light breaks free, victorious. The Celtic festival of Imbolc, celebrated in early February, marks the first stirrings of light returning after the darkness of winter. It's not spring yet, not by a long shot, but the days are getting noticeably longer. Light is winning its slow battle against the dark. Our supernova's first light is similar in spirit, if not in scale. It's not the end of the process, not by far. The remnant will continue to expand and evolve for thousands of years. But this moment, when the light first breaks through, marks the turning point. The star is no longer just dying. It's transforming, giving back, seeding the cosmos with the fruits of its nuclear labor. Japanese mythology tells of the sun goddess Amaterasu, who once hid herself in a cave after a conflict with her brother, Susanoo. The world fell into darkness, and terrible things happened. The other gods tried everything to lure her out, finally succeeding through a combination of clever tricks and the goddess's own curiosity. When she emerged, light returned to the world. The star's light has been hiding in the cave of its own interior, trapped by the density of matter, and now, driven by the violence of the shockwave, it emerges. The universe brightens. The darkness, at least in this small corner of the cosmos, retreats. Aboriginal Australian mythology speaks of the rainbow serpent, a powerful creator deity who emerged from beneath the earth and created rivers, mountains, and all the features of the landscape. The rainbow serpent brought water, brought life, brought colour to a previously barren world. The light emerging from the supernova is bringing its own kind of fertility. The heavy elements created in the explosion will eventually enrich gas clouds, making possible the formation of new stars with rocky planets. Life requires these heavy elements. Water requires oxygen. Organic chemistry requires carbon. Bones require calcium. All of these carried on the light of the supernova, spreading through space. The phoenix is perhaps the most famous symbol of rebirth through fire. This mythical bird, at the end of its life, builds a nest and sets it aflame. From the ashes, a new phoenix emerges, young and vital. Death and birth happening in the same transformative moment. Our supernova is the ultimate phoenix. The star dies, yes. The carefully structured shells are destroyed, the nuclear furnace extinguished. But from that death comes new creation. Heavy elements scattered into space. Shockwaves triggering new star formation. Energy injected into the galactic ecosystem. Death transformed into the seeds of future life. The light that breaks through the photosphere carries information, stories encoded in wavelengths and intensities. Astronomers will study this light, measuring its spectrum, tracking how its brightness changes over time. They'll read the supernova's autobiography written in photons. The early light is dominated by the shockwave itself, the thermal radiation of superheated matter expanding into space. This gives the supernova a bluish color, characteristic of very hot objects. Over the next few weeks, as the outer layers cool, the color shifts toward red. The peak brightness comes a few weeks after the initial breakout, when the expanding material becomes transparent enough that we can see deeper into the ejecta, where the radioactive decay is happening most intensely. This is when the supernova is at its most spectacular, when it's pumping out those 5 billion solar luminosities. After the peak, the supernova begins a long, slow decline. The radioactive nickel has mostly decayed to cobalt, and the cobalt is decaying to iron. The rate of energy production decreases, and the expanding shell continues to cool and dim. Over months and years, the supernova fades, eventually becoming invisible to all but the most sensitive telescopes. But even after the visible light has faded, the supernova remnant continues to evolve. The expanding shell crashes into the surrounding interstellar medium, creating shock waves and heating gas. This can make the remnant visible in X-rays and radio waves for thousands of years. Ancient peoples who witnessed supernovae saw them as profoundly significant events. The Chinese guest stars we mentioned earlier were carefully recorded, their positions noted, their brightness compared to known stars and planets. Some were bright enough to be visible during the day, hanging in the sky alongside the sun like impossible companions. Native American rock art from around 1054 CE may depict the supernova that created the Crab Nebula. The art shows a bright star near a crescent moon, matching the configuration that would have been visible from North America at that time. The star was bright enough to cast shadows at night, an unforgettable sight that was preserved in stone. The appearance of such a bright new star challenged the prevailing worldview that the heavens were unchanging and eternal. Here was direct evidence that the cosmos was dynamic, that change happened not just on Earth, but in the celestial realm as well. Some cultures saw this as auspicious, a sign from the gods. Others saw it as an omen of disaster. We now know that supernovae are neither divine messages nor random catastrophes. They're the natural endpoints of stellar evolution, the inevitable consequence of massive stars burning through their nuclear fuel. But there's still something profound about witnessing one, about seeing a star die and scatter its substance across space. The light breaking through the photosphere is travelling at 300,000 kilometers per second, the cosmic speed limit. Nothing can travel faster. This light left the star's surface and raced into space, spreading outward in an ever-expanding sphere. Some of it heads off into empty space, travelling for billions of years before encountering anything. Some of it strikes nearby dust and gas, heating them and making them glow. And some of it, if there's an inhabited planet within a few thousand light years, enters a telescope and strikes a detector, becoming data for astronomers to analyse. The photons carry their message without loss or degradation. The story they tell is exactly the story of what happened in those final moments, encoded in wavelengths and intensities. It's like receiving a letter from a distant friend, except the letter is made of light and the friend is a dying star. Half an hour has passed since we started watching at 10:30. Half an hour of light breaking through the photosphere, of the supernova announcing itself to the universe. The first photons are already thousands of astronomical units away, racing outward at the speed of light. The supernova is growing brighter by the minute, approaching its peak luminosity. The star that woke up this morning with silicon burning in its core, that collapsed at noon, that sent a shockwave climbing through its interior all afternoon and evening, has finally revealed itself to the cosmos. The light that was imprisoned for 20 million years is free, carrying with it the news of stellar death and the promise of cosmic renewal. From darkness, light. From death, transformation. From the tomb, resurrection. The photosphere has broken, the supernova has begun, and the universe, for a brief moment, has one more brilliant light shining in the darkness. It's 11 at night now, and the supernova has been visible for about half an hour. The light has broken through, the photosphere has been blown away, and now the real work of scattering begins. All those heavy elements forged in the core, created in the shockwave, mixed through the turbulent interior, are now being flung into space at velocities that would make a rocket scientist weep with envy. We're talking about speeds of 10,000 kilometers per second. That's about 3% of the speed of light, fast enough to cross the distance from Earth to the Moon in less than 40 seconds. Fast enough that if you could somehow hitch a ride on an ejected chunk of stellar material, you'd reach Mars from Earth in about 10 minutes, assuming you survive the acceleration, which you wouldn't. The expanding shell of debris is carrying with it everything the star created during its lifetime. Hydrogen and helium from the original gas cloud that formed the star, carbon and oxygen from helium burning, silicon and sulfur from carbon and oxygen burning, iron from silicon burning, and all those exotic heavy elements created in the final moments, the gold and platinum and uranium forged in the shockwave's nuclear fire. This material is spreading outward in an ever-expanding sphere, like ripples from a stone dropped in a pond. Except the pond is interstellar space. The ripples are moving at significant fractions of the speed of light, and the stone was a star containing more mass than our sun. As the ejector expands, it sweeps up the surrounding interstellar medium, the thin gas and dust that fills the space between stars. This isn't a gentle process. The collision between the expanding supernova remnant and the interstellar medium creates shock waves, regions where the gas is suddenly compressed and heated to millions of degrees. These shocks accelerate particles to tremendous energies, creating cosmic rays. Cosmic rays are mostly protons and atomic nuclei travelling at nearly the speed of light. They zip through the galaxy, occasionally striking Earth's atmosphere and creating showers of secondary particles. Right now, as you're listening to this, cosmic rays from ancient supernova are passing through your body. Hundreds of them every second, harmless but constant, a reminder that we're all connected to stellar death. The shockwave from the expanding remnant also compresses nearby gas clouds, and this compression can trigger star formation. Think of it like pressing down on a sponge. When you apply pressure, water squeezes out. When a supernova shockwave hits a gas cloud, stars squeeze out. Well, eventually. Star formation takes millions of years, even when triggered by a supernova. But the process begins with that compression, that extra push that causes parts of the gas cloud to become dense enough for gravity to take over. This means supernovae are not just the deaths of old stars, but the midwives of new ones. The shock from a dying star triggers the birth of the next generation. It's a cosmic relay race where each runner at the end of their leg gives the baton to the next by exploding violently. It's not the gentlest way to pass things along, but it's effective. The heavy elements mixed into the expanding shell are particularly important for this new generation. When the first stars formed in the early universe, they were made almost entirely of hydrogen and helium. Those were the only elements available. But when those stars died and scattered their substance, they enriched the interstellar medium with heavier elements. The next generation of stars formed from gas that contained small amounts of carbon, oxygen, silicon, iron. And when they died, they added even more heavy elements. Generation after generation, the universe has been slowly enriching itself, increasing the abundance of elements heavier than helium. Our Sun is a third-generation star, possibly even fourth or fifth. The gas cloud it formed from had already been processed through multiple stellar cycles. That's why Earth exists. You can't make a rocky planet out of pure hydrogen and helium. You need silicon for rock, iron for the core, oxygen for water, carbon for organic chemistry. All of these came from previous generations of stars that lived, died, and scattered their elements into space. The mythology of sacrifice and fertility appears in cultures around the world, and it speaks to a deep intuitive understanding of how death enables life. The Corn Mother stories are particularly vivid examples. In various Native American traditions, the Corn Mother is a figure who gives her body to feed the people. In some versions, she's killed and buried, and from her body grows the first corn. In others, she instructs her children to drag her dead body across a field, and wherever her flesh touches the ground, corn springs up. It's a disturbing image on the surface, but it captures something true about the cycle of life and death. The star is the cosmos's corn mother. Its body, scattered across space, becomes the material from which new stars and planets grow. The calcium that will one day be in someone's bones, the iron that will one day be in their blood. It's all here in this expanding shell, waiting to be incorporated into new worlds. The Celtic god Dagda had a magical cauldron that could feed any number of people without ever emptying. But some versions of the myth also describe the cauldron as a place of transformation, where the dead could be placed and brought back to life, though changed by the experience. The supernova remnant is expanding like Dagda's cauldron, an inexhaustible source of material for the universe. The dead star has been transformed, its matter reorganized and scattered, ready to feed new creation. In Hindu philosophy, there's the concept of yajna, sacrifice. But it's not sacrifice in the sense of giving something up reluctantly. It's sacrifice as the fundamental principle of the universe. The cosmos maintains itself through sacrifice, through things giving of themselves to support the whole. The sun sacrifices itself by radiating energy. Plants sacrifice themselves by being eaten. Death sacrifices itself by enabling new life. Our star is performing the ultimate yajna. Its entire substance is being given to the cosmos, scattered so widely that it will eventually participate in thousands of new star systems. The sacrifice is complete, total, and it sustains the cosmic order by providing the materials for future complexity. Egyptian mythology tells the story of Osiris, the god who was killed and dismembered by his brother Set. The pieces of his body were scattered across Egypt. His wife Isis gathered the pieces and reassembled him, and from this death and resurrection came fertility and new life. Osiris became the god of the underworld and of vegetation, death and growth intertwined. The supernova is scattering the star's body across light years of space. Eventually, gravity will gather some of these pieces together again into new stars. Not a resurrection of the original star that's gone forever, but new life emerging from scattered death, new complexity arising from distributed simplicity. The Greek story of Demeter and Persephone operates on similar themes. Persephone is taken to the underworld, and while she's gone, the earth becomes barren. When she returns, spring comes again. Death and rebirth, absence and presence, barrenness and fertility, all cycling through the seasons. The supernova marks the universe's seasons in a sense. The long stellar summer of stable fusion, the autumn of advanced burning stages, the winter of collapse and explosion, and the spring of new star formation triggered by the scattered debris. Cosmic seasons playing out over timescales that dwarf human experience, but following patterns we can recognize. Buddhist teachings emphasize pratyasamutpada, dependent origination or interdependent co-arising. Nothing exists in isolation. Everything arises in dependence on conditions, and everything creates conditions for other things to arise. The web of causation extends infinitely in all directions. The supernova demonstrates this interdependence beautifully. The star's formation depended on previous supernovae enriching the gas cloud with heavy elements. Its explosion creates conditions for new stars to form. Those stars will one day die and create conditions for further star formation. Each event depends on what came before and enables what comes after. Nothing exists alone. Everything is connected. The cavity being carved out by the expanding supernova remnant can be hundreds of light years across. That's enormous. A light year is about 9 trillion kilometers. So we're talking about a bubble of hot, expanding gas that spans hundreds of trillions of kilometers. This bubble doesn't expand into perfectly uniform space. The interstellar medium has structure, denser regions and less dense regions, warm gas and cold molecular clouds. When the expanding shell encounters these different environments, it creates complex, beautiful structures. Dense clumps of gas might survive the passage of the shockwave, appearing as knots embedded in the expanding shell. Less dense regions get swept up easily, creating filaments and wisps. The result is a supernova remnant that's intricate and structured, looking more like an abstract sculpture than a simple expanding sphere. The Crab Nebula, the remnant of that 1054 supernova, witnessed by Chinese astronomers, and possibly recorded in Native American art, is a perfect example. Even now, nearly 1,000 years later, it's still expanding, still glowing from the energy of that ancient explosion. Its structure is complex, with filaments and knots and a pulsar at the center, the neutron star remnant spinning 30 times per second. Over thousands of years, the supernova remnant continues to evolve. The expansion slows as it encounters more and more interstellar material. The temperature drops as the energy gets spread over a larger volume. Eventually, after perhaps 10,000 years, the remnant has cooled and expanded so much that it's no longer distinguishable from the general interstellar medium. It's merged back into the cosmic background, its material now thoroughly mixed with the galaxy's gas and dust. But its influence persists. The heavy elements remain, increasing the metallicity of the interstellar medium. The compression it caused in nearby gas clouds may have triggered star formation that's still ongoing. The cavity it carved out affects how gas flows through that region of the galaxy. And somewhere in that enriched material, perhaps millions of years later, a new gas cloud begins to collapse. The gravity that binds the universe pulls matter together, condensing it, heating it, until nuclear fusion ignites and a new star is born. That star's planets, if it has them, will contain atoms that were forged in our supernova, will be built from the scattered substance of our dying star. This is how the universe works. Death doesn't end the story, It changes it, transforms it, sends it in new directions. The atoms that make up your body have been through this cycle multiple times. Every heavy element you contain was forged in a dying star, scattered into space, gathered into a new star system, and eventually incorporated into you. Carl Sagan's famous phrase, "we are made of star stuff," isn't poetry, though it sounds like it. It's literally true. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created inside stars and scattered by their deaths. You are recycled stellar material, ancient beyond imagining, participating in the latest chapter of a story that began billions of years ago. There's something comforting about that, isn't there? You're not separate from the cosmos. You're made of it, shaped by the same processes that shape everything else. The atoms that make you up have been around for billions of years and will continue to exist in one form or another for billions more. When you die, and eventually you will, your atoms won't disappear. They'll return to the environment, be incorporated into other living things, other structures, other stories. You're not permanent, but you're not lost either. You're part of a cycle that's been running since the first stars lit up and will continue until the last stars fade. The seeding is well underway now. The supernova has scattered its elements across a region of space many light years across. Some material is moving fast, some slower, but all of it is enriching the interstellar medium, providing the raw materials for future creation. 45 minutes have passed since 11. 45 minutes of expansion, of scattering, of seeding the cosmic garden with the fruits of stellar death. The supernova is still bright, still pumping out more light than billions of suns, but the peak has passed. From here, it will slowly decline over weeks and months, the radioactive glow gradually fading as the nickel and cobalt decay away. But the important work is done. The elements have been created and scattered. The Shockwave has been launched. The cosmic relay race has passed the baton. Somewhere in the expanding debris, mixed in with the hydrogen and helium, are atoms of gold that will one day be in a wedding ring. Atoms of calcium that will one day be in someone's bones. Atoms of oxygen that will one day be in water, breathed by fish, evaporated by sun, fallen as rain, drunk by animals, incorporated into cells. The star has died, but its legacy is just beginning. The seeds have been scattered. Now comes the patient work of growth, as gravity and chemistry and time work their slow magic, building complexity from chaos, life from lifelessness, consciousness from unconscious matter. The garden has been planted. The future awaits, growing in the dark, nourished by ancient starlight. It's 11:45 at night now, approaching midnight on our cosmic clock. The supernova is still visible, still bright, though beginning its slow fade. The elements have been scattered, the shockwave is expanding, and the neutron star at the centre has settled into its new existence as one of the densest objects in the universe. But the story isn't over. In many ways, it's just beginning. The supernova remnant will continue expanding for thousands of years, creating a cavity in the interstellar medium hundreds of light years across. As it expands, it will compress nearby gas clouds, triggering waves of star formation. Some of those new stars will be massive, living fast and dying young in their own supernovae. Others will be smaller, longer-lived, potentially surrounded by planets where interesting chemistry might unfold. This is the legacy of stellar death. Not an ending, but a transformation that enables new beginnings. The star that died has scattered the seeds for thousands of future stars, each one carrying forward some portion of the original star's substance, each one participating in the ongoing story of cosmic evolution. Let's fast forward a bit in our imagination. It's morning now, 6 a.m. on the day after our star's death. 15 hours have passed since the silicon burning we witnessed at dawn yesterday. 15 hours that contained the entire drama of stellar collapse, shockwave propagation, and explosive dispersal of matter. But out in space, the remnant is still glowing, still expanding. The shockwave has swept up interstellar material, creating a shell of compressed, heated gas. Behind the shock front, the stellar debris continues to expand, carried outward by the momentum imparted during the explosion. Over the next few months, the supernova will gradually fade from view. The radioactive nickel will decay completely to iron. The expanding shell will cool and become transparent. Eventually, only the most sensitive telescopes will be able to detect it, seeing the remnant through X-rays or radio waves, rather than visible light. But the influence continues. The compressed gas clouds, squeezed by the shockwave's passage, begin to collapse under their own gravity. Regions that were stable before are now dense enough for gravitational collapse to begin. Over the next million years, new stars will form in these clouds, their birth directly triggered by our supernova. These second-generation stars will be chemically different from the star that died. They'll form from gas that's been enriched with heavy elements, gas that contains not just hydrogen and helium, but carbon, oxygen, silicon, iron, and all those exotic elements created in the supernova's final moments. This chemical enrichment matters profoundly. It changes what kinds of stars can form, what kinds of planets can condense from the leftover material, what kinds of chemistry can happen on those planets. Consider our own solar system's formation, which happened about 4.6 billion years ago. The gas cloud that collapsed to form the Sun and planets contained elements from many previous supernovae. We know this because we can measure the isotopic ratios in meteorites, the primitive rocks left over from the solar system's formation. Some isotopes found in meteorites have abundances that only make sense if a supernova occurred nearby, right before the solar system formed. The shockwave from that supernova may have even triggered the collapse of the gas cloud that became our solar system. We might literally owe our existence to a dying star, whose explosion set in motion the chain of events that led to the Sun, Earth, and eventually to you. The heavy elements in that ancient supernova debris eventually condensed into rocky planetesimals. Those planetesimals collided and merged, forming larger bodies. After millions of years of this cosmic demolition derby, 4 rocky planets emerged: Mercury, Venus, Earth, and Mars. Earth, third rock from the Sun, formed from material that contained silicon for rock, iron for the core, oxygen that would eventually combine with hydrogen to make water, carbon that would become the foundation of organic chemistry. All of these elements came from stars that died before our Sun was born. Resurrection myths appear across human cultures, and they speak to a deep hope that death is not the final word. Christianity has the resurrection of Christ on the 3rd day. Egyptian mythology has Osiris, murdered and dismembered, but brought back to life by Isis. The phoenix rises from its own ashes, the Hindu concept of reincarnation, where the soul takes new forms after death. These myths aren't scientifically accurate descriptions of what happens to human consciousness after death, but they capture something true about the physical universe. Matter doesn't disappear when a star dies. It transforms, it scatters, it recombines into new forms. The resurrection is real, though it happens to atoms rather than souls. The Buddhist concept of rebirth operates similarly. Consciousness continues, but not in the same form. Each rebirth is influenced by the karma, the actions and patterns of previous lives. But each new life is genuinely new, not simply the old life continuing. Our supernova's atoms are being reborn into countless new configurations. The iron that was in the star's core might end up in a planet's magnetic field, protecting life from cosmic radiation. The gold created in the shockwave might sit in a gas cloud for billions of years, before being incorporated into a planet's crust, mined by some future civilization, and made into something beautiful. Each atom's journey continues, influenced by its past but open to new possibilities. The Native American concept of the seventh generation is relevant here. The idea is that when making decisions, you should consider how they'll affect the next 7 generations. It's a long-term view, recognizing that actions have consequences that ripple forward through time. Our supernova's influence extends far beyond 7 generations. The heavy elements it scattered will participate in countless stellar generations, each one benefiting from the enrichment provided by stars that came before. The shock wave it generated might trigger star formation that continues in waves for millions of years. The cavity it carved out might influence how gas flows through that region of the galaxy for tens of millions of years. One action, one stellar death, rippling forward through cosmic time, affecting events billions of years in the future. The Celtic festival of Samhain, celebrated in late October and early November, marks the end of the harvest and the beginning of winter. It's a time when the boundary between the world of the living and the world of the dead becomes thin, when ancestors can be honoured and death can be contemplated without fear. There's wisdom in this seasonal acceptance of death as part of the cycle. Winter comes, yes. Things die, yes. But spring follows winter, and new life emerges from old death. The cycle continues, and death is not an ending but a transformation. Our supernova marks a kind of cosmic Samhain, the end of one stellar harvest, and the beginning of the winter that will eventually give way to new stellar spring. The boundary between death and life becomes thin, and we can see clearly how they connect, how one enables the other. The comfort in understanding stellar death this way is profound. Death, at least at the cosmic scale, is not a failure or a tragedy. It's a necessary part of the creative process. Without stellar death, there would be no heavy elements. Without heavy elements, there would be no rocky planets. Without rocky planets, no complex chemistry. Without complex chemistry, no life. You exist because stars died. The very atoms that make up your body required stellar death to be created and scattered. Death is written into your origin story at the most fundamental level. And when you die, your atoms will continue. They'll return to the environment, be taken up by other organisms, scattered by decay, eventually perhaps subducted into Earth's mantle or blown off into space by a meteor impact billions of years from now. Your atoms have been through multiple cycles already and will continue cycling long after any memory of you as an individual has faded. There's a strange comfort in that continuity. You're not permanent as a configuration, but you're permanent as matter. The atoms that briefly came together to form you will persist, carrying no memory of you, but carrying forward the same physical properties that made you possible. The Hindu concept of moksha, liberation from the cycle of death and rebirth, represents the ultimate spiritual goal in some traditions. The individual soul merges with Brahman, the ultimate reality, losing its separate identity but gaining unity with everything. In a physical sense, atoms achieve a kind of moksha when they are incorporated into a black hole's event horizon, or when the universe eventually reaches heat death in the impossibly distant future. But until then, they cycle through forms, participating in the cosmic dance of creation and destruction. The Christian idea of eternal life, of death being overcome through resurrection, can be reinterpreted in physical terms. The atoms that made up people who lived thousands of years ago are still around, still participating in life, still part of the ongoing story of matter in the universe. In that sense, nothing truly dies. Forms change, configurations dissolve, but the underlying substance persists eternally. The Egyptian concept of the eternal cycle, where the sun dies each night and is reborn each morning, where the Nile floods and recedes in predictable patterns, where death and rebirth are woven into the very fabric of existence, captures something essential about the universe. Stars die, but star formation continues. Elements are scattered, but they recombine into new structures. Energy dissipates, but new concentrations emerge. The universe is not running down toward a heat death as quickly as early thermodynamics suggested. It's more complex than that, with local decreases in entropy balanced by increases elsewhere, creating pockets of order and complexity, even as the overall trend is toward disorder. You're one of those pockets of complexity, an unlikely configuration of matter that achieves the remarkable property of being able to contemplate its own origins. You're the universe becoming aware of itself, looking back across billions of years of cosmic history and understanding, at least partly how you came to be. The elements in your body were forged in stellar furnaces like the one we've been watching die all night. The calcium in your bones created in silicon burning during a star's final hours. The iron in your blood created in the same process, possibly photodisintegrated back to lighter elements during collapse, possibly reformed in the shockwave, scattered into space, gathered into a molecular cloud, condensed into rocky planetesimals, incorporated into Earth, taken up by your body through diet. Every breath you take contains oxygen atoms forged in stellar cores. Every thought you think occurs through electrical signals mediated by sodium and potassium ions created in supernovae. You are, quite literally, made of recycled stars, ancient beyond imagining, yet participating in the latest chapter of a story that spans the history of the universe. The gardening metaphor that runs through this chapter is deliberate. Gardeners understand that death feeds life, that last year's leaves become this year's soil, that the cycle continues and each generation builds on what came before. The supernova is the ultimate composting, breaking down stellar material into its constituent elements so they can be incorporated into new growth. It's messy, it's violent, but it's also essential. Without it, the cosmic garden would be barren, containing only hydrogen and helium, incapable of supporting the complex chemistry that makes planets and life possible. So we return to where we began, standing inside that furnace, watching the final day of a star's life unfold. We've followed the silicon burning at dawn, the iron accumulation in mid-morning, the catastrophic collapse at noon, the shockwave climbing through the afternoon and evening, the light breaking through as night fell, and the scattering of elements that continues even now. It's morning again, a new day in our cosmic cycle. The star that woke up yesterday is gone, transformed into a neutron star surrounded by an expanding cloud of debris. But its legacy continues, written in the atoms it scattered, in the star formation it triggered, in the enrichment of the galactic ecosystem it participated in. And somewhere in that expanding debris, mixed with hydrogen and helium and cosmic dust, are the atoms that will one day be you. Not you specifically, perhaps. That depends on timing and location and a billion other factors. But atoms like you, atoms that will participate in future chemistry, future planets, future life. The cycle continues. Death enables life. Destruction creates the conditions for new creation. The end is also the beginning, And the story goes on, written in starlight and supernovae, in the slow, patient work of gravity gathering matter together and the spectacular violence of explosions scattering it apart. You are part of this story, not separate from it, not observing it from outside, but woven into it at the most fundamental level. The atoms that make you up have been through this cycle multiple times already, and they'll continue cycling long after you're gone. There's profound comfort in that cosmic perspective, in understanding your place in this ancient ongoing story. You're temporary as a configuration, but eternal as matter. You're insignificant on cosmic scales, but miraculous in your complexity. You're the universe's way of knowing itself, of looking back across billions of years and understanding, however imperfectly, how it all works. The star has died. The seeds have been scattered. The new dawn has come. And the garden grows on, nourished by ancient starlight, reaching always toward new possibilities, new complexities, new forms of existence we can't yet imagine. Sweet dreams, fellow travellers through space and time. You're made of star stuff, and you carry within you the legacy of countless stellar deaths and births. May you rest well knowing that you participate in something vast and ancient and beautiful, something that will continue long after any individual star or planet or person has faded from view. The cosmic garden awaits, growing in the dark, reaching toward the light, nourished by the deaths of stars and the patient work of time. Sleep well, children of supernovae. Your elements were forged in fire, and they'll return to the cosmos when your temporary configuration dissolves, ready to participate in whatever comes next in this ancient, endless dance of death and rebirth. The dawn is broken, the story continues, and you are part of it now and always. So here we are, at the end of our journey through the final day of a dying star. We've watched silicon burn in the early morning hours, seen the iron core grow heavy with its own success, witnessed the catastrophic collapse at noon that compressed a solar mass into the size of a city in less than a second. We've followed the shockwave on its journey upward through the star's layers, watched it forge gold and platinum in temperatures hotter than anything since the Big Bang, seen it break through the photosphere in a burst of light that briefly outshone a galaxy, and we've contemplated the scattering of elements into space, the seeding of the cosmic garden that will eventually grow new stars, new planets, perhaps new forms of life. It's a lot to take in, this story of stellar death. The timescales involved, from 20 million years of patient burning compressed into a single cosmic day, to the fraction of a second during which the core collapsed. The energies involved, enough to vaporize planets, to create elements that couldn't exist under any other conditions, to send shockwaves racing through hundreds of light years of space. But perhaps what's most remarkable is how intimately connected you are to this story. This isn't ancient history happening far away to something that has nothing to do with you. This is your origin story, written in nuclear physics and scattered starlight. Every atom in your body heavier than hydrogen was created inside a star. The carbon that forms the backbone of every molecule in your cells, the oxygen you're breathing right now, the calcium that gives structure to your bones, the iron that carries oxygen through your blood, the trace elements like zinc and copper and selenium that your body needs to function. All of it was forged in stellar cores and scattered by stellar deaths. You're made of recycled stars. This isn't a metaphor. It's not poetic exaggeration. It's a straightforward statement of fact that happens to sound like poetry. The atoms that make you up are ancient beyond human comprehension. They're older than Earth, older than the Sun, older than the solar system. They've been through multiple stellar generations, cycled through stars and supernovae and gas clouds, gradually climbing up the periodic table from simple hydrogen to the complex mix of elements that makes life possible. And they'll continue their journey long after you're gone. The atoms that briefly came together in the specific configuration that is, you will dissolve back into the environment, be taken up by other organisms, scattered by geological processes, perhaps eventually incorporated into new stars billions of years from now. Your existence is temporary, but your substance is eternal. You're a wave in the ocean of cosmic matter, rising briefly into a complex form before subsiding back into the undifferentiated whole. The wave is real while it lasts, but it was never separate from the ocean. There's something deeply comforting about understanding death this way. At the cosmic scale, death isn't an ending. It's a transformation, a rearrangement, a necessary part of the creative process that keeps the universe interesting. Without stellar death, the universe would still be full of hydrogen and helium, the simple elements created in the Big Bang. There would be no carbon, no oxygen, no silicon, no iron. There would be no rocky planets, no liquid water, no complex chemistry, no life. The universe would be simpler perhaps, but also infinitely more boring. Stellar death is what makes complexity possible. It's what allows the universe to explore new configurations of matter, new possibilities, new forms of organization, from simple to complex, from undifferentiated to structured, from lifeless to alive. The progression depends on stars dying and scattering their enriched substance into space. You are the beneficiary of billions of years of stellar death. Countless stars lived, burned through their nuclear fuel, and exploded so that the atoms that make you up could be created. You literally owe your existence to stellar sacrifice, to the deaths of stars you'll never see that happened before your planet even formed. And in a sense, you're participating in the same process. You're a temporary concentration of order and complexity in a universe that tends toward disorder. You're processing energy, creating structure, maintaining the unlikely configuration that makes you you, and when you die, that concentrated order will dissipate, the energy will scatter, and your atoms will be available for new configurations. It's the same pattern at different scales. Stars concentrate matter and energy, maintain complex internal structures for millions or billions of years, then die and scatter. Living things do the same, just much faster. Concentrating nutrients, maintaining complex biochemistry, then dying and returning their substance to the environment. The pattern echoes through all levels of existence: birth, life, death, rebirth, concentration, complexity, dissolution, recombination, the eternal cycle that keeps the universe dynamic and interesting. The timescales are what make it hard to grasp emotionally. Stellar evolution happens so slowly that we can't directly observe most of it. We see snapshots, individual stars at different stages, and piece together the story. But each star's journey from birth to death spans timescales that dwarf human history. Yet those vast timescales are real, and they matter. The star we watch die today began its life 20 million years ago. 20 million years of steady hydrogen burning, of maintaining the delicate balance between gravity and fusion pressure. And then, in less than a day by our cosmic clock, that entire structure collapsed, exploded, and scattered. 20 million years of construction, one day of destruction. But that destruction enabled creation on a grander scale, seeding space with the materials for thousands of future stars and countless planets. You exist in this moment because of events that happened billions of years ago. Stars that died before Earth formed, created and scattered the elements that eventually became you. And you're connected forward in time too. The atoms you're made of will participate in events billions of years in the future, long after the sun has become a white dwarf, and the Earth is a cold, dead rock orbiting a stellar remnant. That continuity, that connection across cosmic time, is what makes the story of stellar death ultimately hopeful rather than tragic. Individual stars die, yes. Individual living things die, yes. But the substance persists, the cycle continues, and new possibilities keep emerging from old endings. So tonight, as you drift off to sleep, you might take a moment to appreciate the stardust you're made of. The calcium in the bones of your hand, forged in a star's final desperate hours of silicon burning. The oxygen in the breath you're taking, created when helium nuclei fused in a stellar core. The iron in your blood, possibly photodisintegrated and reformed multiple times during stellar collapse and explosion. You are ancient starlight given temporary form. You are the universe becoming aware of itself. You are the latest chapter in a story that began with the Big Bang and will continue until the last star fades. And that story, for all its violence and drama, for all its destruction and loss, is ultimately a story of creation, death enabling life, endings enabling beginnings, simplicity giving rise to complexity. The stars that died for you scattered their substance so you could exist, and when you return your atoms to the cosmos, they'll be available for whatever comes next in this ancient, endless dance. Sleep well, knowing you're part of something vast and beautiful and ongoing. You're made of star stuff, and you'll return to star stuff, and the cycle will continue, as it has for billions of years and will for billions more. The cosmic garden grows on, nourished by stellar death and tended by time itself, and you, for this brief moment, are part of that garden, a flower blooming in the light of ancient supernovae. Sweet dreams, children of stars, may your rest be peaceful, and may you wake tomorrow with wonder at the cosmic story you're participating in, written in atoms and starlight, spanning the history of the universe, continuing forever. Clear skies and gentle sleep, the sleepy astronomer.